Okay, with this lecture, I would like to go over some of the cloud computing facilities that we have available, and specifically I want to talk about Google Earth Engine. So cloud computing, you're all aware of it. Essentially, it provides us on-demand availability of computing resources. There's lots of players on the cloud computing market. They can be cost effective. Essentially, instead of having our own little cluster or big cluster, depending on how much money you've got, we can outsource the system administration, upgradability. Obviously, Google or Amazon, they will upgrade their computer, so we have access to the newest architectures. So as I said, lots of players, but the ones that have to do with Python and are amenable to that, that I want to focus on are Google Colab, which hopefully we'll have some time to go over in class. But in essence, it's Jupyter notebooks on the cloud with a free GPU. And free CPU, which can be really great if you're doing, for example, any machine learning. Then there's Google Cloud. I've linked to some articles here how you can set up your own Jupyter server on them. Amazon Web Service, Azure Binder is a service where you can have your notebook on GitHub, for instance, and you can share it, and then they can run it directly. So you can just pass a link, and it can run on a cloud instance. So there's an older link for Colaboratory here that gives you a little bit more details, and there's also something called Kaggle kernels, which are again geared more towards the data science machine learning. All right, now in terms of the other things we can do on the cloud, apart from setting up our own Jupyter service, and this is closer to what Google Colab does, is some of the types of analytics that we'll see later in this lecture. And the framework that is, I guess, the more applicable or for the type of work we do, especially if you're dealing with satellite remote sensing data sets, is Google Earth Engine. And Google Earth Engine has many data sets. So here you can see a catalog, and they keep adding data sets, and especially lately they've been adding a lot of model output. But you get both the type of imagery that you would get from different satellites. So you got Landsat, Sentinel from European Space Agency. You've got some other static data sets, land cover, terrain. So again, you've got multitude of types of data sets available already. So no download necessary, and you can perform some of the processing. Excuse me, you can perform some of the processing on the cloud. So one of the interfaces you can use to access Google Earth Engine, and this is under, well, let's use another account here. So you can just log in with your UMass account directly, and what it will do is it will take you to the authentication page, which is not letting me do that. So I'm just going to use my Gmail account here, which is not letting me. In any case, so the browser is not really want to work with me, but if you just click on that link, you should be able to access that. So if it doesn't work with your browser, try a different browser. Sometimes I get that with Chrome, sometimes with Firefox. So these things happen. But it doesn't really matter, because what we're going to do is actually use the Python API to access Google Earth Engine. So this would be the command to use to install the libraries we need, and primarily it would be the Earth Engine API and also Folium, which is one of the ways we can produce maps and interactive dynamic maps on the web. Now there's a newer library that I haven't looked into that much, but it seems to have a lot of promise. It's called GEEmap. So what this is, it provides a lot of interactivity, and it seems to gotten to the point where it's pretty mature. But again, I haven't had the never had to really interact with it, but it seems to be like a really good library for this type of thing. And the author has been really fantastic in providing video tutorials, documentation, and so forth. So definitely check it out. But if you do not want to do that, then you can just do what we're going to do in today's lecture. So after you've installed the Earth Engine API, then you need to run this command with, again, the exclamation mark, because it's a shell command, it's a system command. So Earth Engine authenticate, which what it will do is it will take you to an authentication page from Google. So it will ask you to copy long string, and which you can then paste again, which essentially will create the credentials. So you won't have to do that again. So if you do it once, then you won't have to do it again whenever you import the EE module, which is the Earth Engine module. So every time that we import the Earth Engine module, we have to initialize it. So let's just test the installation. And the way we're testing this is we are initializing, and then we're grabbing a map of elevation, global map of elevation, and we're just going to look at the information for that. So as with everything in Python, everything's an object. So, and then we also have the modules. So E is a module, SRTM is the object. So you see how it has the methods, but then also we're calling the, it's an Earth Engine image. So let's run that. And you should get something like this. So it is a dictionary, so it's like the JSON format, but it really is a dictionary. So it tells us the type, it tells us how many bands it has, it gives us the which is a list, so it has the ID of the band, the data type, and so forth. And you get the projection information, the time of acquisition, and all that. All right, so everything works. And as I said, we can use either volume or GE map for visualization, but a lot of the times, if we have something relatively simple or even complex, or if you're more familiar with JavaScript, you can use the code editor directly. But if you're not and you want to use Python because you're dealing with some other data sets that you can access with Python, and because you learn Python in this class, you can just use the API. So let's take a look at how we would do, how we produce a map. And I'm providing a snippet here. And we haven't really talked about classes, but it's sort of beyond the scope of what we've talked about so far. But it's if you remember again the cats and dogs example we used at the beginning of the semester, and we had the animal and then cat and dog would inherit some of the properties of the parent object. Essentially, we're doing the same thing here. So the only difference is, so we're essentially saying, hey, I want you to create a type of volume map, but I'm going to add a function to it which did not exist in the parent object. So EE map is a volume map, but it has this extra function. And you don't have to worry about the details. I can't even remember where I stole this from, but basically what this does is we can provide it with an image object, same as the SRTM from before, some visualization parameters, a name, and what it will do is it will produce a volume map instance that grabs the data on the fly from Earth Engine. So let's run this and successfully. So if we try to use the EE map object that we just created with no zooming, we'll get the global extent, and sometimes we don't want to do that. So we can use things like points. So Earth Engine provides a set of geometry constructs. So we have geometry, and then we've got points. And actually, let's take a look at what you can get. So let's see, geometry, and again, tab completion is our friend. So you can see we get a bunch of different things here. So there's definitely, there we go, multi-point, multi-polygon, polygon point, rectangle. So you can see all the functions that are available. So we create a point at these coordinates, which, as you probably guess, is Amherst. And then we create a buffer around that. And the buffer is 500 kilometers, and we get the bounds. So from the point, we use the buffer method, and then we get the bounds of that because the buffer will just give us a polygon. But what we want is the bounds, and the bounds, then we want to grab the coordinates. So I suggest you actually perform these chained operations one by one to see what you get from each one. But this whole line here will just give us the coordinates. And it would be interesting if we want to run this and we want to look at what the region Amherst area looks like. You see we get this list of the bounds. So it's a polygon. So this first line is the same as the last line because we want to close the polygon. Otherwise we have this rectangle. So we start 1, 2, 3, 4, and then again we close the polygon. So this is what it looks like. But now let's look at a map. And the way we look at a map is, again, is we use the EE map object that we created. So if we do that, we pass the location and then we create a starting zoom. So if we don't add any layers to it, this is what we're going to get. So you see the center is going to be right at that location, but we get the other niceties of being able to zoom, pan, and so forth. Now, what we're going to do is we're going to add a layer. And again, remember, this function is not available in the volume map object, but it is available in our derivative EE map object. So with that, we're passing the image. We're passing some visualization parameters, telling it, I want the minimum value, I want the maximum value. There's some other things we can define. Take a look at the Google Earth Engine documentation for that. And then we're giving it a name. So if we run this, again, you see now the elevation and then the base map underneath. Now, the really nice thing about this is that the data are being acquired on the fly. So the same thing we would do with Google Earth, we're seeing it here. So now you see the resolution changing, hopefully at least. You see it sort of, getting a bit more detailed. And then if we zoom out, again, you see how we're grabbing each tile separately, because that's how they're stored on Google servers. All right, so fairly simple, to get a map and show it. And again, we can go to the different data sets that we have. So click on the link here to get the data catalog that we saw from before. And let's try to get the top of atmosphere reflectance data from Landsat 8, which the Landsat program I'm sure you've heard about. It's pretty much the longest running satellite with different sensors. We're up to 8 right now. And we're getting the top of the atmosphere reflectance. It's in the, in the visible spectrum, what we're going to be looking at. So you'll see how we're going to look at the red, green, and blue, but you'll also get some, infrared, near infrared bands, depending on your application. Those might be useful. So the way we can get this now, SRTM was an image because it's elevation. So it was acquired in 2000. So we only get the data from one pass, essentially. But with something like Landsat, we get an image collection because we get data every 16 days. So instead of image, we get image collection, and we have, again, you'll see the specific format that the string needs to have. So we have the Landsat collection / LC8, L1T, and those refer to the products. So tier 1 product, but then we want the top of the atmosphere. So, and everything again is lazily evaluated. So you see that it was very fast. We didn't download anything, but L8 now points to that collection. But let's assume that we want to actually get a specific year. So in this case, we're going to get 2013. So we grab, there's some nice convenience functions, one of them being filter date. So we provide the starting date, the ending date, and then let's look at the get info function. And again, because it's a function, you see that we need the parentheses pair inside that. And we got an error. Oh, it's too many. I see. Okay, so one of the things we're gonna do, let's see here. Let's, so the error, and this is a common error, and you see it. You see the message here: collection query aborted after accumulating over 5,000 elements. So because they're free resources, there's some limitations to it. So what we're gonna do, and let me see how I named the. We have the region Amherst area. So we have the point here. So remember this variable. This is the point. What we're going to do is actually use another filter option. And you see there's a filter bounds. So what filter bounds is going to do is it's only going to get the images that intersect where these points fall within, essentially by intersection with the point. So let's see if this works, and we're still filtering with the date. And there we go, much faster. We get the info for our images. So we have a set of images. But again, we only grab the ones within that time frame of 2013 that intersect our point. So again, if you get the error that we got from before, just know that it's based on the quota that Google Cloud has, and we need to further filter our collection to be able to see these. All right. So now let's mosaic the images. So let's combine them, and we're going to do that by applying a median filter. So every pixel in our image is going to have the median value from all the images that were available into 2013. And this, instead of a collection, will give us back an image. And you see this here. We just get an image. And these are all the bands that are available. We have band 1. Band 2, 3, all the way to, let's see, I mean, there's some quality control bands here that we also get, but we get all the way to band 9. Actually, no, this is Landsat, my apologies, this is Landsat 8, so we get more bands than Landsat 7. So we get 10, band 11 here. All right, so now let's create a map of the median image. And again, we create E map object at that location. And we now, instead of SRTM, we add the L8 image median composite that we had. And you'll see that it's gonna be, again, calculating on the fly. So we've got the image, and again, these are all the images that intersected that point, that center that we had here, so this point. And that's the reason why we do not get any images here, because all the images that did not intersect that point, they're not available. So if an image intersected, we get the image, well, and then, you know, its extent. So that's why we get things that are not just at this point. But if this image, for example, did not intersect, and it didn't, we do not get it in the collection. And you'll see that even clearer if we do zoom out. And now, again, you can guess why this looks like this, because it's how basically depends on the orbital characteristics of the satellite itself. So as it's going like this, you know, it maps the Earth's surface, and we're getting images that intersect that point. Okay, but hopefully you've seen how simple it is, and that image didn't really show us anything, you know, because again, it's a median of all the bands together. And it's using the first 3 bands, and they really don't look like anything that we could recognize. However, if we just grab the red, green, and blue bands, so B4, B3, B2, and we pick appropriate minimum and maximum values, and we say, well, this is a true color image, and we do the same thing again. Let's look at what we're going to get this time. There we go. So now, hopefully, you agree with me that this looks like something the satellite would actually see. Well, at least in terms of a true color image. And again, if we zoom in, we're gonna get slightly better resolution, as you can see here. So, well, this white is clouds. So let's go to the part that's not cloudy and start zooming in even more. And you see now how the resolution gets better, so the image gets sharper. Okay, but now sometimes again we need to create what's called a false color image, and now we're going to use the B5 band, B4, B3, and those you can easily see what they are. What did I do? Okay, you know what? Even if I wanted to do this, I don't know how I did it. So let's see here. All right, let's go back to where we were. All right. So the way you can see it is just you can find all this information with the band designations for the Landsat satellites. So you see how we're using. You see we have Landsat 1 through 5, 4 to 5, 7. So you'll get some of this information. So if we're using the 432, remember the true color, we get red, green, blue. However, if we use 543, we get near infrared, red, and green. And for some applications, it's what we need. And I think there's another page where it essentially tells you there we go, the common combinations. That will tell us, will give us some information about this. But let's take a look at this. So what we're going to do is we're going to have the true color image. We're going to have the false color image. But the difference here also is that we're adding a layer control, which is a child to the image itself. So this is the command we need for that. And if we run it, you'll see the difference that we get here. So we get this layer control, so we can toggle images, and then you see that we get the base map from OpenStreetMap. So again, lots of different combinations we can have depending on our application. All right, now let's talk a little bit about how we would do time series analysis with Landsat data. And the way to do this is by utilizing Matplotlib in this case. So we're going to do this in a simple way, and we're going to import datetime, NumPy, Matplotlib dates, and the end dates as the well, in essence, I mean, these are essentially the same, but sometimes it's, I wanted to show both how you can use an alias for that. So let's define the bands that we want. So we have time would be the X band, and then the Y band list, we grab the first 5 bands of the Landsat image, or collection actually, because we're going to do a time series. So in this case, let's not pick the 2013, let's pick from 2014 to 2017. And I forgot to run this, so let's run this. So let's get a filtered image collection from Landsat 8 and get a specific point. So now we're not going to use the top of the atmosphere reflectance, we're going to use the surface reflectance. And you'll see here that we're getting a collection, and we're filtering the dates from start time and end time, which we have defined before. One thing we want to do is we're going to pick Death Valley. Just want to show how stable it is in terms of reflectance. And we're saying, here's the point. And we can either define it as an e-geometry point like we did before, but I also wanted to show a different way we can do this, where we can have a dictionary or essentially a JSON data structure that Earth Engine likes. And what we do is we have a collection, and we say get the region 500 meters around that point. So let's run this, and info, essentially it will grab everything that we need. So let's look at what's contained in info. So let's look at the header. The header is going to be the first element of info. And you see here we got ID, longitude, latitude, time, the bands, all the bands, and then some of the quality control bands here. But what we can do is we can grab the data from info from the second row onwards, or from the second element onwards. And you see we got 203 rows and 16 elements, 16 columns, which are these 16. So it almost is as it almost is as if we use pandas to read this. So that's how we get the info. Now this is where it gets a little bit tricky because we need to convert the timestamps. Google Earth uses nothing that we can identify as a date, but Python can. So the way to do it is to use the headers index, which is time, and then remember the list comprehensions. So this is a little bit complicated, but stay with me. All right, so we have a list comprehension where we're looping through, because the IT essentially gives us if we go back, we need this column here, the fourth column, but because sometimes it changes, we want to make sure that we grab, so IT would be 3 essentially, the fourth column, but we need this to be dynamic, and hence why we use the header index here. So the time would be, and again we're grabbing the fourth column of the data, we convert it into a float, and then we say create dates from the timestamp that's in I, so containing data, but then divided by 1,000. And that's really the format we need for converting the timestamps to a date. So to make Python and Google Earth talk to each other. So you see here we're getting year, month, day, hour, minute, second. I think is this millisecond, I believe. So very accurate, but again, we're getting the dates that we need that correspond to the data. So let's grab the data that we want. So our wideband list, remember we had B1 all the way to B5. So we're skipping some of the other bands and also the quality control bands. So our data are going to be from data, and we are getting the header as well. That's contained, well, not the header. We're getting from the first column, so we can do this. I bands, so these are the indices of the bands. And then we're making sure that we're getting a float array. So let's look at that, and you see we're getting the surface reflectance values. All right, so now let's import our matplotlib, create a figure, add the subplot, which is 111. And then what we're going to do is we are going to plot time versus the data in circle with symbols, and then we're changing the color. So band 3, band 4. Let's put the legend, turn on a grid, and have the band values, and we get something like this. Now there's another way we can do this, of course. If instead of creating instead of just sticking with the NumPy array, we convert something into a Panda. We create a Pandas data frame, and we can easily do that. I wanted to show this alternative way, but this is something that we can definitely do, because then it opens up possibilities to use Seaborn and so forth. So last thing I wanted to show is let's calculate a vegetation index. And you've probably heard about the NDVI, which is the normalized difference vegetation index. It's given by this ratio of the difference between the near infrared minus the red channel, and then the sum of those two channels in terms of reflectance values. So we're going to grab band 3, band 5, and band 5 is near infrared, band 3 is red. So again, look up the designations of the different bands to be able to know which one you need to grab, and it's really as easy as getting the justice ratio. But what this will do is it will provide information about the vegetation state. So what we're doing here is, and because we want to make sure that we sort the times to create a time series, and again, this is where pandas would come in handy. But in case you want to use matplotlib and NumPy directly, again, you just have to add these extra steps, which really just shows us the extra steps that we're avoiding when we're using these other nicer and user-friendlier libraries. So again, we create a figure, add a subplot, sort the times, and then we have time, NDVI, I, and the only reason that we are sorting the times because we also want to pass a line. So not just the marker, but also we want to line through them. And let's do that, and here we go. So this will give us the NDVI index, which again, depending on the season, we have green and not so green. So again, it will allow us to do things, again, look at vegetation health, for instance. But what if we want to look at an NDVI image? So we saw that we had essentially downloaded the data. We had it in NumPy format, we could have had it in the data frame, and we know how to calculate things. But how about we calculate something directly on the cloud, on the image? And this is where we're using the Google Earth Engine API, but within Python. So we define a function that says add band NDVI. So it takes an image as an input argument. And from that image, it selects the red channel, which is, as we saw, B3, the near infrared, which is B5. Now, we cannot just do simple arithmetic like, red minus NIR minus red divided and the rest. But what we can do is we can use the methods that are within these image objects, which is NIR subtract red. So that would be the B5 minus B3. And then all this divide by the sum of these. So this here is essentially the NDVI calculation, but it also carries the metadata that are associated with the bands. And because we're combining these bands, it will grab the metadata from the first available band, which is NIR. We don't want that because we want to rename it. So we can chain that function here. So we do .rename NDVI. And then what we do is we return the original image, but with an extra band of NDVI. Sometimes you might just want to return the NDVI image, which is fine, but you lose all the information from the original image. So we could just return the entire image, but with a new band. So let's run this, and we define that function. And the reason why we define a function is because we want to tell Google Earth Engine to, hey, map this function over the entire collection. And again, we couldn't use the map functionality if we did not have a function here. So we couldn't really pass, NIR and minus red and the rest of the calculation. But having the function, then the function operates on each image of the collection. So we're mapping the function over all the images in the collection. And we say, well, this is NDVI. So if we then print and we select just the NDVI band, because remember, we get images that are that have all the bands, but with an extra band of NDVI, and then we get the region around the point, 500 meters, the same thing we did before. But this, you see now how it gives us the data that we have available for the NDVI band. So let's visualize the map. So again, because we have a collection of NDVI images, we get the composite. So let's also pick the median composite, create a map around the Amherst location. Now we want to get from -1 to 1. We're changing the palette here to make it look a little prettier. We name it NDVI, and let's look at our map. I remind you, the calculations are being done on the fly on the cloud, and there they are. So they start showing up. You see the river and lakes are showed up as white, but if we start zooming in, you see the resolution will again, the image gets sharper, but the calculation is being done on the fly. But you see now, look at this tile finished. And everything is lazy and it doesn't get calculated until we need it. But now you can start seeing some of the details here that we can see. And again, very, very quickly. We have not only we have access to lots of satellite data without the need to download anything, but we can also perform some relatively simple processing. So as long as it's a calculation that can be done separately per pixel, it will be relatively efficient. And not only that, but we can also look at the images and map them fairly quickly. And with that, I'm going to finish. Hopefully this, again, just gave you an idea of Google Earth Engine and its abilities, but also gets us in the habit of realizing that a lot of the calculations we can do can be done on the cloud.